Welcome to The Story of Us. I'm your host, Madison Reed, and today we're embarking on an extraordinary journey through the most complex object in the known universe, the human brain. Right now, as you listen to these words, 3 pounds of neural tissue inside your skull are performing feats that would make the most advanced supercomputers weep with envy. But here's the thing that will blow your mind. We almost didn't make it. The story of human intelligence is not one of inevitable triumph, but of a risky evolutionary gamble that could have easily failed. Today, we're going to explore why our brains grew so massive, what hidden instincts drive our behavior, how deception shaped our intelligence, and what this all means in our age of artificial intelligence. So settle in, because we're about to uncover the secrets of what makes us uniquely, brilliantly, and sometimes dangerously human. If exploring the true roots of intelligence, risk-taking, and adaptation fires up your curiosity, check out Skoob, the AI-powered podcast app with access to 1,500-plus expertly curated podcasts based on the world's top nonfiction books. From evolutionary psychology and decision science to the future of AI, Skoob connects you to fast, fascinating insights tailored to your passions. Download Skoob from the App Store or Play Store and unlock a universe of knowledge where risk leads to discovery and every episode is a leap forward in understanding. So let's begin. Let's start with a puzzle that has baffled scientists for decades. Picture this. 2.5 million years ago, our earliest human ancestors walked the African savanna with brains about 600 cubic centimeters in size. That's roughly 3 times the size you'd expect for a mammal their weight. Fast forward to today, and modern humans sport brains averaging 1,200 to 1,400 cubic centimeters. Our Neanderthal cousins? Even bigger. But here's what's truly mind-boggling. This massive brain expansion was an evolutionary gamble that should have killed us. Think about it this way. Your brain right now represents only 2 to 3% of your total body weight, yet it's devouring a staggering 25% of your body's energy when you're at rest. Compare that to other apes, whose brains consume just 8% of their rest time energy. It's like running a sports car engine in an economy vehicle. The fuel costs are astronomical. This wasn't just about energy either. Carrying around this massive brain required significant biological compromises. Our ancestors had to spend more time and effort seeking food, and their muscular strength diminished. It was like a government reallocating funding from defense to education. We literally redirected energy from our muscles to our neurons. The result? Sure, a chimpanzee can't win a debate with you, but it can absolutely tear you apart in a physical confrontation. For over 2 million years, our ancestors walked around with these energy-hungry brains, but with little more to show for it than some basic stone tools. The question that haunted researchers was simple. Why did evolution favor such an expensive organ for so long before it paid off? The answer, as we'll discover, lies not in our relationship with the environment, but in our relationships with each other. But first, let's talk about another unique human trait that emerged alongside our growing brains: walking upright on 2 legs. This bipedalism gave us distinct advantages. We could scan the savanna for prey and predators, and crucially, it freed up our hands for complex tasks. This led to an interesting evolutionary feedback loop. As our hands became more dexterous, the concentration of nerves and finely tuned muscles in our fingers increased. This anatomical development enabled humans to perform incredibly intricate tasks. The earliest evidence of sophisticated tool production dates back 2.5 million years, and archaeologists actually use tool creation as a key criterion for identifying ancient human species. So we had the big brains and the nimble hands. But something was still missing from this picture. The real breakthrough in understanding human intelligence came from an unexpected source: the study of liars and cheats. Before we dive into the dark arts of deception that shaped our minds, let's talk about something equally fascinating and far more hidden: the instincts that control us every single day. Right now, as you listen to this, You're under the influence of programs that you never learned, never chose, and can barely perceive. These are your instincts, and they're far more numerous and powerful than you might imagine. Consider this. When a foal is born, it struggles to its feet within minutes and can run with the herd within hours. No learning required. It's all hardwired. We humans like to think we're different, that we operate on reason and intellect while animals operate on instinct. But here's where it gets interesting. William James, the brilliant 19th century psychologist, turned this assumption on its head. He argued that humans aren't special because we have fewer instincts than animals. We're special because we have more of them. Many more. The reason we don't notice these instincts is precisely because they work so well. They process information effortlessly and automatically, like the unconscious expertise of a master tennis player or a chicken sexer who can determine a chick's gender in seconds, but can't explain how they do it. These instincts represent ideas so advantageous that they've become encoded in our DNA through millions of years of natural selection. The individuals who had the best survival and reproduction-enhancing instincts were more likely to pass on their genes. James suggested a mental exercise to reveal these hidden drivers. He called it making the natural seem strange. Why do we smile when pleased instead of scowling? Why does speaking to a crowd feel so different from talking to a friend? Why does a particular person leave us completely enraptured? We might say it's obvious that we smile, that our heart races before crowds, that we love someone because they're perfect for us. But as James pointed out, to a lion, it's the lioness who seems made to be loved. To a bear, the she-bear. A nesting hen would find it inconceivable that any creature could be indifferent to the allure of her eggs. From this perspective, while some animals' instincts might seem baffling to us, our instincts are equally inexplicable to them. We're all running sophisticated programs that we barely understand. The thing is, these programs come with a cost. What researchers call instinct blindness. We can't consciously access these systems any more than we can consciously control our reflexive tennis serve. They're too important to be left to conscious interference, which would likely disrupt rather than enhance their performance. Sexual attraction, fear of the dark, empathy, jealousy, fairness-seeking, problem-solving, incest avoidance, facial expression recognition. All of these rely on neural networks so finely tuned that their seamless operation goes completely unnoticed. The seemingly simple acts we take for granted are actually neurally sophisticated processes intricately woven into our biological fabric. This sets the stage for understanding one of the most important theories about human intelligence, a theory that suggests our remarkable cognitive abilities didn't evolve to help us understand the physical world, but to help us navigate something far more complex and dangerous: each other. In 1976, a scientist named Nicholas Humphrey completely revolutionized how we think about human intelligence with a simple but profound insight. He looked at the classic Robinson Crusoe story and realized that most people were focusing on the wrong part. Everyone assumed that Crusoe's intelligence was being tested by his isolation on the island, figuring out how to make fire, build shelter, find food. But Humphrey argued that the real intellectual challenge began when Man Friday showed up. Suddenly, Crusoe had to communicate, cooperate, and, crucially, figure out whether he could trust this other intelligent being. Now imagine if Crusoe couldn't trust Friday. Then he'd need his wits about him constantly. Multiply this scenario with additional people, and the mental demands escalate exponentially, requiring higher-order thinking and sophisticated social intelligence. This insight led to what's now called the social intelligence hypothesis. The idea that our remarkable cognitive abilities evolved not to solve practical survival problems, but to navigate the incredibly complex social world of our ancestors. Think about it. While making tools and climbing trees to escape predators require intelligence, they don't necessarily demand creativity. These techniques, once discovered, can be easily copied, but dealing with other intelligent beings who are simultaneously your allies and competitors, that requires a completely different level of cognitive sophistication. Humphrey's theory lay dormant for years until two young primatologists, Richard Byrne and Andrew Whiten, decided to test it in the 1980s. They focused on something that had been largely ignored by science: deception among primates. Their research revealed a fascinating catalog of trickery in the animal kingdom. A young baboon, caught misbehaving by several elders, suddenly pretends to see a predator, causing the adults to forget his transgression entirely as they scan for threats. Two young chimps hide their food-gathering activities from a dominant male to avoid having their hard-earned meal stolen. A female baboon manipulates a male into chasing away a competitor by pretending to collaborate with him, only to abandon the alliance once she's secured feeding privileges. Initially, the scientific community was reluctant to publish these findings. The idea that animals routinely deceive each other was frankly unflattering. But nature doesn't reward honesty. It rewards survival and reproduction. Consider the eastern hognose snake, which feigns death when threatened. The mimic octopus can transform into at least 15 different sea creatures. Female plovers perform elaborate broken wing displays to lure predators away from their nests. The mirror orchid attracts male wasps by mimicking female wasps, tricking them into spreading pollen without providing any actual reward. The breakthrough came when Franz de Waal published Chimpanzee Politics in 1982, documenting the manipulative power dynamics within a zoo's chimpanzee colony. His vivid descriptions of alliance formation, strategic violence, and deceptive reconciliations gave credibility to studying primate deceit. Inspired by this work, Byrne and Whiten published Machiavellian Intelligence in 1988, creating a taxonomy of deceptive behaviors: teasing, pretending, concealing, and distracting. Their thesis was that human intelligence's roots lie in social manipulation, deceit, and cunning cooperation. But they still needed hard evidence linking deception to brain size. Enter Robin Dunbar from Liverpool University, who made a crucial observation. Across primate species, brain size correlated with social group size. Larger groups required more cognitive resources to manage complex social dynamics. Dunbar found that neocortex volume was directly proportional to group size. This held true for humans as well, suggesting an optimal social group size of around 150 members, a number that appears consistently across human societies, from hunter-gatherer tribes to modern military units and organizations. The final piece of evidence came when Byrne and researcher Nadia Korp directly linked neocortex size to deceptive behavior across primate species. The frequency of deception correlated perfectly with brain size. Species with larger neocortexes, like the great apes, displayed the highest instances of deceit. This research revealed a fascinating truth. Evolution favored deceptive capabilities reflected in brain size. The species with the most advanced social manipulation skills gained the upper hand. While Byrne didn't measure deceit directly in humans, our exceptional ability for deception being well established, the research confirmed the complex interplay between intelligence and social dynamics that has defined our evolutionary journey. In essence, we became intelligent not because we needed to understand rocks and trees, but because we needed to understand each other. And that understanding often involved figuring out when someone was lying to us, or when we needed to lie to them. So we've established that human intelligence evolved through a complex dance of social manipulation and cooperation. But this raises an obvious question. What exactly is intelligence anyway? This seemingly simple question has sparked decades of debate. Is intelligence about thinking quickly, reasoning ability, memory, vocabulary, mathematical skills, mental energy, or perhaps just intellectual curiosity? Here's what's fascinating. People we consider highly intelligent often show surprising weaknesses in certain areas. They might have poor general knowledge, lack practical cunning, or even walk into lampposts. Meanwhile, someone with a poor academic record, say a soccer player, might possess the acute ability to assess a complex field situation and execute a perfect strategic pass in a split second. This led researchers like Howard Gardner to propose multiple intelligences, the idea that different talents represent distinct abilities. Musical aptitude, language fluency, spatial reasoning, and social understanding don't necessarily align with each other. Robert Sternberg took a different approach, categorizing intelligence into three types: analytic, creative, and practical. Analytic intelligence deals with problems designed by others, clearly defined challenges with all necessary information provided, single correct answers, and detachment from daily experience. Think school exams and traditional IQ tests. Practical intelligence, on the other hand, requires you to identify and define problems yourself. These problems are often ill-defined, may lack crucial information, and can have multiple solutions. Here's where it gets interesting. Brazilian street children, despite performing poorly in school mathematics, show remarkable mathematical skills in their everyday contexts. Professional horse race handicappers' abilities aren't predicted by their IQ scores. Zambian children excel at intelligence tests using wire models, but struggle with pencil and paper tests, while English children show the opposite pattern. But here's where the story gets more complex. In 1904, statistician Charles Spearman made a crucial observation. Children who perform well in one subject tend to perform well in others. This suggested that different types of intelligence aren't completely independent. They're correlated. Spearman coined the term general intelligence, or G, to describe this phenomenon. Some statisticians argue that G might be just a statistical construct, while others consider it a quantifiable measure of what we commonly perceive as cleverness. Regardless of the theoretical debates, G proves to be a reliable predictor of academic performance over time. The evidence for general intelligence is compelling. The speed of information retrieval correlates with IQ scores. General IQ remains relatively stable across different ages. While intelligence grows rapidly between 6 and 18, a person's IQ relative to their peers changes minimally. Most remarkably, even an infant's speed of habituation to new stimuli correlates significantly with later IQ, suggesting we might be able to predict adult intelligence based on infant behavior. IQ scores show strong correlations with school test results, indicating that high IQ children tend to absorb more of what schools teach. However, this doesn't mean education is predetermined. Considerable variations in average academic achievement across different schools and countries demonstrate the potential impact of quality teaching. The key insight is that intelligence genes require environmental stimulation to manifest fully. It's like having a high-performance engine that still needs quality fuel and proper maintenance to reach its potential. This understanding of intelligence becomes crucial when we consider our place in the cosmic community. Are we alone in the universe with our particular brand of intelligence, or might there be other forms of cognition out there among the stars? As we contemplate our own intelligence, a tantalizing question emerges. Are we alone? The search for intelligent extraterrestrial life forces us to think about intelligence in cosmic terms. If intelligent aliens exist in our galaxy, they likely experienced an evolutionary trajectory similar to ours. They probably evolved from non-intelligent life forms and encountered various existential risks: climate changes, asteroid impacts, resource depletion, perhaps even the development of dangerous technologies. Here's the intriguing part. For these beings to have developed into a civilization capable of traversing the galaxy, they must have successfully navigated through all these risks. Whatever form their cognitive capacities take now, they would likely not be dominated by false beliefs or dangerously aggressive tendencies. While this isn't a certainty, it does decrease the likelihood that they would pose a threat to us. This reasoning suggests that initiatives like messaging to extraterrestrial intelligence, ME-TI, might not be as risky as some fear. Like entrepreneurs announcing their presence in the market, it could be beneficial for us to signal our existence to the cosmos and hope that some advanced civilization takes notice. But here's the challenge. Both the search for extraterrestrial intelligence, SETI, and METI rely heavily on the longevity of intelligent civilizations. Intelligence might have arisen multiple times across our galaxy, but very few of these species might exist concurrently. Think of it this way. Imagine 50 people are invited to an evening party, each arriving at a randomly chosen time. Whether they find a vibrant gathering or an empty room depends entirely on how long each person stays. If everyone stays for just 1 minute, most arrivals will find emptiness and conclude no one else came. But if guests stay for an hour or two, many will overlap, creating a lively affair. We're uncertain about the typical lifespan of intelligent civilizations. The Milky Way is roughly 13 billion years old and has probably been capable of supporting intelligent life for about 10 billion years. If humanity endures as a technological species for 10,000 years, this would be like attending a 6-hour party, but staying for only 1/50th of a second. Even if thousands of other intelligent civilizations arise during this time, our brief presence likely wouldn't overlap with theirs. To discover other intelligent life, we need to assume both frequent occurrences of such life and extended sustainability of civilizations. There's reason for optimism about frequency. Current estimates suggest roughly 40 billion planets within the Milky Way could be conducive to life. Earth's history shows that life emerged relatively quickly after the planet's formation. If Earth is typical, then life, including intelligent life, could indeed be widespread. The real question becomes, how long do intelligent civilizations typically last? Do they destroy themselves shortly after developing dangerous technologies? Do they transcend their biological origins and become something unrecognizable? Or do they simply lose interest in cosmic communication? These questions about alien intelligence bring us full circle to examining our own cognitive abilities. What makes human intelligence special? How does it compare to the artificial intelligences we're now creating? And what might this tell us about the potential for intelligence elsewhere in the universe? As we develop artificial intelligence systems that can beat us at chess, recognize faces, and even generate human-like text, a crucial question emerges. What exactly makes human intelligence special? The answer, it turns out, is both humbling and remarkable. Let's start with learning abstract concepts. While artificial neural networks can quickly analyze images and identify objects, they often latch onto superficial statistical associations rather than genuine abstractions. A neural network might identify a cat based on fur texture or pointed ears, but completely fail to recognize the same cat if those features change slightly. This leads to bizarre vulnerabilities. Small modifications to an image, altering just a few pixels or adding a sticker, can completely fool advanced AI systems. Meanwhile, humans effortlessly correct initial recognition errors through additional cognitive processing. Douglas Hofstadter, the cognitive scientist, humorously suggested that the real challenge for AI isn't defeating humans at Go or chess, it's recognizing the letter A in all its myriad forms. Human brains effortlessly generalize abstract concepts across diverse contexts, a capability current AI still lacks. Then there's the efficiency problem. AI systems are astoundingly data-hungry compared to human learning. Contemporary neural networks require millions of examples to grasp a domain, while humans learn from comparatively minimal data. A DeepMind system needed 900 hours of gameplay to achieve proficiency in Atari games that a human would master in about 2 hours. Language acquisition provides an even starker example. Children in environments with limited verbal communication, like among the indigenous Tsimane people, still achieve linguistic competence comparable to children in linguistically rich environments. Top-tier AI systems from major tech companies require exponentially more data to reach even moderate language proficiency. Human brains showcase unparalleled efficiency, extracting maximum learning from minimal input. We can often learn something new from a single experience and seamlessly integrate it into our existing knowledge framework. Introduce a new verb like purge it, and humans can intuitively use it in various contexts, automatically applying linguistic rules for conjugation and usage. This connects to something profound. Humans exhibit what philosophers call systematicity, the ability to identify and apply abstract principles across different contexts. Understanding that every number has a successor reflects an abstract concept of infinity that can be vastly generalized. We naturally seek patterns and integrate symbols and rules in ways that current AI cannot replicate. Jerry Fodor theorized about this language of thought, emphasizing its recursive nature. This enables humans to create and utilize infinite combinations of ideas fluidly. Current AI models, focused primarily on deep learning, struggle with this fundamental capability. Perhaps most importantly, humans can recombine learned skills to address new problems flexibly. Learning arithmetic can be repurposed for calculating bills, solving complex mathematical problems, or even understanding musical rhythms. This recombination of skills into new complex tasks is something neural networks fundamentally struggle with. AI systems like AlphaGo are highly specialized and fail to apply their expertise outside narrowly defined parameters. They lack the flexibility to generalize knowledge across different contexts or recombine learned skills to solve novel problems. There's also something uniquely human about social learning. We share and propagate knowledge through language in ways that current neural networks simply cannot. While AI knowledge is embedded as patterns of synaptic weights, human brains can consciously articulate knowledge, efficiently conveying complex information in succinct phrases. The human brain seems to have evolved specialized circuits that automatically operate according to intrinsic computational structures. Areas like Broca's region enable the integration and abstraction of concepts in ways not observed in AI models or other species. We cannot help but recognize patterns in sounds, integrate abstract ideas, and apply symbolic rules. These are the cognitive singularities that define human intelligence. As we reach the end of our journey through the landscape of human intelligence, let's take a moment to appreciate the extraordinary story we've uncovered. We began with a mystery. Why did evolution favor such expensive, energy-hungry brains for millions of years before they paid obvious dividends? The answer led us through a fascinating web of discoveries. We learned that our brains didn't grow large to help us master the physical environment, but to navigate the treacherous social world of our ancestors. The Machiavellian Intelligence Hypothesis revealed that deception, cooperation, and social manipulation drove the expansion of our cognitive abilities. We discovered that beneath our conscious reasoning lies a vast network of instincts, sophisticated programs that guide our behavior in ways we rarely recognize. These hidden puppet masters shape everything from our facial expressions to our deepest attractions, operating with such seamless efficiency that we remain largely blind to their influence. We explored how intelligence itself defies simple definition, encompassing everything from abstract reasoning to practical problem solving, from rapid data processing to creative insight. The correlation between different cognitive abilities suggests a general intelligence factor, yet the diversity of human talents reveals the multifaceted nature of mind. We pondered our cosmic loneliness and the possibility that intelligence might be common in the universe, but fleeting. The longevity of civilizations may determine whether we ever make contact with other intelligent beings, or whether we remain isolated signals in the cosmic dark. Finally, we examined what makes human intelligence unique in an age of artificial intelligence: our ability to learn from minimal data, to generalize abstract concepts, to recombine skills creatively, and to share knowledge socially reveals cognitive capabilities that current AI systems are nowhere close to matching. The story of human intelligence is ultimately a story of contingency and wonder. We are the products of an unlikely evolutionary gamble that paid off spectacularly. Our brains are biological masterpieces, capable of pondering their own existence, creating art and music, solving mathematical theorems, and reaching toward the stars. Yet we remain, in many ways, prisoners of our evolutionary heritage. The same social intelligence that enabled our success also burdens us with jealousy, tribalism, and deception. The instincts that guided our ancestors' survival sometimes lead us astray in modern environments. As we continue to develop artificial intelligence and search for signs of cosmic intelligence, we gain new appreciation for the remarkable accident of consciousness that occurred in the brains of a particular species of African ape. We are neither the inevitable outcome of evolution nor its final destination, but rather a fleeting moment of self-awareness in the universe's long story. The Intelligence Chronicles continue to unfold, written in the firing patterns of neurons, the algorithms of machines, and perhaps in signals from distant worlds. Our journey of understanding has only just begun, and the most exciting discoveries likely lie ahead. Thank you for joining me on this exploration of the human mind. Until next time, keep questioning, keep learning, and remember, the most sophisticated computer in the known universe is sitting right between your ears, contemplating its own existence through your consciousness. That's a miracle worth celebrating. This has been The Story of Us, and I'm your host, Madison Reed, reminding you that intelligence isn't just about being smart, it's about being human. If this episode opened your eyes to the complex, messy, and miraculous journey that made us who we are, don't forget to like, follow, and subscribe on Spotify, Apple Podcasts, YouTube, or wherever you listen. It's the best way to stay connected as we continue unraveling the incredible threads of our shared human story. And for even more fascinating dives into the science of mind, evolution, technology, and identity, check out Skoob, the AI-powered podcast app with access to over 1,500 curated episodes rooted in best-selling nonfiction. Whether you're curious about brain science, consciousness, or the future of human potential, Skoob makes learning fast, deep, and unforgettable. Download Skoob today from the App Store or Play Store and keep exploring what it truly means to be human. Until next time, stay curious.